In the first part of section 48, we will look at limits and continuity a second time. We want to remember that the limit is the intended height of a function, so it's what it is approaching. And this is a review. So if I'm looking at the limit of f of x as x approaches -4, I'm going over to -4, and I want to make sure that from the left side and the right side, they're basically connected to the same point. And wherever that is, that's going to be my answer. So if you can look at that and just tell that it's at 2, that's great. Or you can actually write this out and you can say that from the left it's going towards 2, from the right it's also going towards 2, and because they're both going to that same value, that is our limit. Now another thing we want to talk about, which is a review, is continuity. So if I'm looking at -4, I want to say, is it continuous or not? And at -4, we would say that it is continuous because you can evaluate it at -4 and the limits meet, and the value that we would get when we evaluate it matches up with the limit there. For number 2, we're going to look at 0. Now at 0, again, if I'm looking at the left side and the right side here, they're both going to that same open circle. And that open circle is at 1. So if you can look at that and just say that it's 1, that's great. Or if you want to actually write this out and say from the left, it's approaching 1. From the right, it's also approaching 1. And because they're both approaching the same value, the limit is going to be 1. Now, when we look at continuity though, the limit matches, but it's an open circle there, which means that you can't actually evaluate f of 0. And because of that, we have a type of discontinuity, and this one is point discontinuity. And you do want to remember that we've looked at 2 types in the past. We've looked at point discontinuity and we've also looked at jump discontinuity. What's going to be introduced today is infinite discontinuity. Now for number 3, we're looking at 2. At 2, again, I want to look from the left, it's going towards this open circle right here, and that's at 2. From the right, it's going towards this closed circle right here, which is at 5. And because these 2 sides don't match, I'm going to have to say DNE for the limit. Now again, we could actually write out that on the left side, it's going towards 2. On the right side, it's going towards 5. And then again, because they don't match, we say DNE. Then we want to talk about continuity. Again, as soon as there's no limit, it's going to be a type of discontinuity, and that type is going to be jump. Now take a look at -3. So at -3, I'm going to move just to the left, and I see that on this side it's approaching positive infinity. On the right side of -3, it's approaching negative infinity. So because they are not both approaching positive infinity or both approaching negative infinity, we have to say DNE on this one. And again, here's the example on the left. It's going to positive infinity because it's going up towards that asymptote. And on the right, it's going to negative infinity because it's going down towards that asymptote. Therefore, we say DNE. Now, as far as continuity here, there is a break in the graph, and we've talked about this, and when we see an asymptote here, what that's going to be is infinite discontinuity. For number 5, we're looking at -1. Now again, I go to -1 and I'm going to move just to the left. Just to the left, it's going towards positive infinity. Just to the right, it's going towards positive infinity as well. It's okay that these arrows are not lining up. They're both going towards positive infinity. So because they're both going towards positive infinity, our answer is positive infinity here. And as far as continuity here, we still have a type of discontinuity, and that discontinuity, again, at that asymptote is going to be -1. So anytime we have a vertical asymptote, we can make the conclusion that it's going to have infinite discontinuity there. It could still have a limit. We saw that in this one it didn't have a limit, it was DNE, but in this one it did have a limit. Now we want to talk about when does this happen algebraically. Well, algebraically, we can see this with rational functions, and this is what we did in Unit 7. So a rational function is a quotient of polynomials such that the denominator has a degree of at least 1. Here are 3 examples. What I'd like you to do right now is pause the video and go ahead and factor anything that you can factor in all of those problems. Now here are the factors that we're going to get. In number 6, factoring just the denominator gave me x plus 2 times x plus 3. 7, I can only factor the denominator to x plus 1 and x plus 3. And in 8, I can factor both the numerator and denominator, and you can see those factors here. Now, going to number 6 for now, I want to look at what kind of excluded values we're going to get. Since the denominator can never be 0, in number 6, I'm going to say that -2 and -3 would both be excluded values, things that would make our denominator a 0. So since our excluded values are -2 and -3, we could say that f of x is discontinuous at -2 and -3. Now, as far as implications for this with continuity, at -2, because this would cancel right here, that -2, and I'd encourage you to write that right next to it, is going to be point discontinuity. It would cause us to have an open circle on our graph. And at -3, because that's going to have a vertical asymptote at -3, that's going to be infinite discontinuity there. Now for number 7, again, our excluded values here, they should be -1 and -3, and we can say that g of x is discontinuous at -1 and -3. Now again, I want you to think about what types you have here. Rational functions aren't going to give you jump discontinuity. So we're really only looking at where are we going to have point discontinuity and where are we going to have infinite discontinuity. So go ahead and classify which one is which there. And again, remember, asymptote is what's going to give you the infinite discontinuity. So since this one's going to cancel, the x plus 3's, its associated value, this one, is going to be our point discontinuity. And because our vertical asymptote would be at -1, that's going to be our infinite discontinuity. Then finally for number 8, here what I have is it's discontinuous at both 2 and -1. So I can state h of x is discontinuous at 2 and -1. And then again, I want to think about any implications here. So x plus 1 can cancel in the numerator and denominator. That's going to give me point discontinuity at -1. And because the asymptote would be at 2, that one's going to be infinite discontinuity. Now we have a few more problems to look at. On number 10, we're going to start by considering what any excluded values would be. There's nothing to factor here. So if I set x minus 2, and I technically can do that twice, and say that it cannot equal 0, I'm going to get 2 as an excluded value. That would be considered a vertical asymptote according to what we've done previously. And what we learned today then is that means that there's infinite discontinuity at x equals 2, and that our vertical asymptote is at x equals 2. Take a look at number 11 and consider any type of discontinuity and implications of our graph. Now on this one, technically, one thing we can consider is to get common denominators here. That means that we would be multiplying the numerator and denominator by x plus 1. That's going to give me 2x plus 2 in this numerator plus 1, so I'm really getting 2x plus 3, and that would be over x plus 1. Now, that didn't change my denominator at all. So really, looking at it here, I can just consider the fact that -1 is the only excluded value here. And because that x plus 1 isn't going to cancel, I can classify that as being a vertical asymptote at -1. And that means we have infinite discontinuity. And again, we would say the vertical asymptote is at x equals -1. Now this one has some factoring to do. So go ahead and factor this. Decide what kind of discontinuity you might have here, and this would be a good time to pause the video. So when we factor this function, we should have the following. At that point, I can decide that I have excluded values at both 3 and at -1. Now because x minus 3's would cancel, that tells me that I would have a hole or a point at 3. And so we're going to call that point discontinuity at x equals 3. And then from there, if you're finding the hole, which eventually is going to be important, what we would do is we would take that 3 and we're going to plug it in for all of the x's in the result. So x minus 3's have canceled, so I'm really just plugging it into 3 minus 2, so 1, divided by 3 plus 1, so 4, and that's where I'm getting that 1/4 from. And that would be that ordered pair where that hole would occur. The other type of discontinuity we're going to have here is going to be at -1. Again, we know that because that x plus 1 would still be in the denominator, -1 is a vertical asymptote, therefore we have infinite discontinuity there. Do the same thing for 13, go ahead and factor do any reducing, try to come up with the excluded values and state their types of discontinuity. Again, this would be a good time to pause the video. So here are the factors that we're going to get for 13. Again, when I look at excluded values here, this is going to be 1. This one is going to be -3. Now, because these can cancel, I'm going to say that at -3, I have point discontinuity. Then I want to plug that -3 back in. Now remember, this part is canceled, so I'm just plugging it in for these two x's. So if I do that, I'm going to get -6 minus 1, so -7 in the numerator, divided by -3 minus 1, so -4 in the denominator. The negatives will then cancel, and that's where I'm getting 7/4 from. And then my other type of discontinuity here is going to occur at +1. Again, there's a vertical asymptote there. That means that it's going to be infinite discontinuity at 1. And that wraps up what we're going to cover for today's lesson. You're going to complete the first portion of the homework assignment in section 48 as well as the exit slip associated with this lesson.